Okay, so welcome everybody. My name is Miguel Santos, and well, my background is in physics. So I am a physicist or former physicist that at some point left physics and went into bioinformatics and biophysics for quite some years, kids. And then I decided to change a little bit life and looked into some possibilities of setting up a startup that involved machine learning things, which is not surprising. Whatever you do ends up dealing with these things nowadays. So, well, basically that's a brief summary of who I am. This chapter is a little bit, I think it's a little bit theoretical or philosophical at some points, because the discussion of why we need a random variable, or why we need probabilities to describe things, it's a bit probably obvious to everybody. What I would say would be the main point of this chapter would be actually the last section, which is structured probability models, and so we will go through some basics that probably everybody at some point have seen. We would refresh them a little bit. And I hope you have comments that will make it more interesting than what I have to say here. Well, in terms of why we need probabilities, I think I would say there are 3 points. One is that you have events that are intrinsically random. So the arrival of customers at the service desk is something that you cannot describe in a way that is deterministic. That means deterministic means something like the following that I'm writing here. So if this f is something, this function is something like any trivial function that we would have seen at school, everybody has an idea of what is a deterministic function. So this would be a deterministic function for each value of x. You know exactly the value of y. This is not something that you can expect in the general case, and reasons for that is because, well, the process is random. The book mentions something like quantum phenomena that are intrinsically random. It's not a matter of knowledge that you're missing, it's because it is random. But for the things that are more interesting in our case are real life cases where maybe we could imagine that if we know everything, we could come up with such a function, but the system is simply too complex, and we cannot deal with all the variables that would be necessary to describe it. So we end up using just a limited amount of features, and that's something that most of you are already have already experienced. As soon as you have a limited amount of features of an event of a process that that is more complicated, you are missing information, and any prediction that you will do with those limited amount of features will give you only approximate results to the actual values, and therein lies the variability that you will observe. This variability, in mathematical terms, the best way to describe it is through probabilities. So that is why we see a chapter on probabilities. And examples would be throwing the dice or tossing the coin. More elaborate examples would be something called like random set of events, which is the queuing problem. So you may have the case that there is no customer arriving, and this is, imagine this is a full day, so a big interval of time. It could be that nobody comes. It could be that only one comes. It could be that two come with this interval between them. It could be that two come with this other interval and at this other time. It could be that five come, and so on and so forth. So this is another type of random process that could happen, and probability is the way to describe it. So actually, this is a big of a change in mindset, because the deterministic case is a nice function. You can even often invert that function, and it's a one-onto-one mapping. And in the probabilistic case, the change of mindset is that you do not know this, and the only thing, the most you can know about the random variable is a probability distribution. And well, that is what you have. So a function that will give you something like the following. Imagine that you have a dice, and you throw the dice, 6 possible results. The only thing that you can say about this variable, this random variable, is, well, what is the probability of each of those results, for instance, and nothing else, in the sense that the probability contains all the information about the random variable. The book goes on, makes some distinctions, which is namely, usually the probability that everybody has seen is the definition of probability as from a frequentist approach, and that would be this result. So if the dice is unbiased, we do not know nothing, so it's 1/4 the probability of each of the individual results. We want that probability to always have some nice properties. That's what you already may know. So that is a positive number. It's 0 only if the case is never happens. It's impossible. It's 1 if the case is, well, for sure, that is the only case that happens. We also have I would say that it's convenient to remember a couple of properties. And one is in case of 2 events. Here, in this case, is the set of dice results 1 and 2, or 3, 4, and 5. So in this case, I'm interested only when it's a 1 or a 2. In this case, if it's 3 or 4. And what I'm asking is, what is the probability that I have either a result in this set or a result belonging to this set? So in the case when these 2 events, S1 and S2, do not have anything in common, then the probability of the joined event is the sum of the probabilities. And the other important result, or the other important property, sorry, is that if you have 2 sets, in this case, imagine 1, 2, but S2, sorry, I should say here rather maybe S3, because otherwise would be confusing. So if you have, yes, thanks. That's obviously, there is here a mistake, and somebody pointed that out. It's not 1/4, but 1/6. Okay. And so if they are, if they exhaust all the possibilities, the 2 events, so let's say S3, it would be 3, 4, 5 and 6, and S1 is S1. And they are not sharing anything, intersection 0. So the probability of the join event, which would be the sum, because they are independent, would be equal to 1, which means that the probability 1 means that, well, it's for sure that one of the possible events will happen. That is what the normalization means. Or in other terms, that this set describes all the possible cases that may come out. And if that's not the case, then your description is wrong, and you should update your description. That's all. So I think I would leave rather the discussion of marginal probabilities and conditional probabilities, or even the chain rule for conditional probabilities, to the discussion that I have later on structured probabilistic models. And this is so because this is actually, for me, it's actually the part that summarizes everything that, or the most important thing of this chapter. So as Armando told me, everybody is expected to have gone through the chapter. I didn't plan on going through each of those sections in detail, and I would wait for discussions or questions, particular questions, to show up in the chat room. So so let's see some probability distributions. One, I will jump now to point 3.3, probability distributions. And for instance, in the discrete case, this would be actually the probability distribution of the dice, in the case that the dice is unbiased. So I would write it in a general way as okay. So the probability of any of these events is 1/6, and this summarizes everything about this random variable. If we are dealing with a bias dice, then eventually we could come up with individual probabilities that are away from the 1/6, with the condition, though, that the sum of all those 6 probabilities have to be equal to 1. So let's let's concentrate now on a continuous variable. So in the case of a continuous variable, the variable can take up well, continuous values, the real numbers, and not integers. And then what we have is a continuous function describing the probability. Well, okay, let me put it in another way. This would be the probability density function. And they distinguish between probability density function, probability mass function, being the probability mass function for discrete variables. And in the case of continuous, they say probability distribution density function, because in this case, the probability of, let's say we are studying the heights of a given population that is bound between 150, 140, and 1 and 230 meters. Okay, so this would be a continuous variable. But now here is one question that I'm sure many of you have it clear. Sorry. What would be the probability that one person picked up at random would have a height of 1/6? So if you think about it, in the case of a continuous variable, the probability of picking up exactly 1/6 would be 0. And this is so because, well, we have an infinite range of possibilities, even within 1.4 and 2.3. So from the point of view of the frequentist approach, the number of cases we are interested in would be 1. The number of possible cases would be infinite. So the only way to make sense of this is to say that this is equal to 0. So what can we say then about a continuous variable? The only thing that we can say is that I've been writing here a capital, but maybe I should write lowercase p, because usually the capital P is reserved for the discrete case. So the only thing we can say is that is the following. This is the only thing that makes sense, which means what is the probability? Let me write it here more clearly. This is meant to be an interval between h and delta h. Okay. Okay, so for if you are considering the probability of a variable of the height, let's say the probability that the height is 1/6, but actually between 1/6 and 1/8. So this would be 0.2. Then there is a meaning for that, and the meaning is really a probability, but only if you consider this expression, which is the probability density of 1/6. Let me put it here in the specific case. So the probability of h being 1/6 times the interval we are considering, say 0.2, this is a finite probability. I keep forgetting here the dot. Let me put a dot here. Okay, this would be a finite probability that is this thing. Okay, that most likely will be positive. I mean, not 0. There will be somebody with this interval of height. So in the case of continuous variable, the only thing that makes sense is considering the probability within a given interval of the range of the variable, but not a specific value, because that's 0. And this is why to the P of X, we call it density, and not a probability mass distribution. Keep Okay. Okay, so so one of the possible probability distributions that everybody knows is the Gaussian distribution. And the Gaussian distribution is, in the one-dimensional case, could be written, let me see, okay, and here divided by, okay, 2. Okay, so we have an exponential, and the exponential, I'm missing here parentheses, sorry, let me see. And the exponential is divided by a number, and if you try to normalize this, which means if you do okay, so if you do this integral in all the range of the variable x, let's assume the range is from -infinity to +infinity, then you will find that indeed the integral amounts to 1, so it's properly normalized. This is the Gaussian distribution, and in Python we can plot it nicely. It looks like that. Everybody knows more or less like how it looks. So let me comment now on something that the chapter discusses as well, which is fine. All the information of the variable, of the random variable, is contained in the probability distribution, but often you do not know it. You just sample data. So how can you get information about the probability distribution? And the answer about that is on calculating what's called moments of the variable. If you can, let me say exactly what moments are. Sorry, it's not what I wanted. This is code. Okay, so for instance, one of the possible moments of a random variable would be the mean, and the mean is calculated as okay, or the expectation value of the random variable x. Oops, this should be marked down. Sorry, 1 second. This is not showing now as Markdown. It's not picking up now the LaTeX code, but I think you see what I'm trying to do here. So in the case of a continuous variable, you integrate the probability density times the variable, and that gives you the expectation value. You have also something that would be the expectation of a difference, which is the following difference. Okay, so this means we would be in the integral would contain, instead of the x, it would contain this, oops, 1 second, I'm missing here something. It would contain the square of that difference. So that difference is each value minus the mean, the expectation value of the variable. That should be capital X. So this would be integral of okay, now it happens. And this is called the second moment. And you can calculate further moments of the variable. Simply, I will copy this because it's the same. But instead of 2, you take any moment of this difference. So these are centered moments of the random variable. You take each random value that if you are doing this, for instance, in a sample, then you have instead of an integral, you have a sum. Instead of a density, you have a mass probability distribution. But the idea is the same. You take each value, you subtract the average, and these difference you exponentiate to n, being that 2, 3, 4. And if you have all possible moments, you also have all the information about the random variable. You also have all the information about the probability distribution. And this is the relation between moments and statistics that we can gather from a random variable, and the function that contains in itself all the information, which is the probability distribution. So that's why we always go and get immediately the average, get the variance, because it gives you a hint on the probability distribution itself. Usually people just calculate the average and the mean and the variance. But eventually you can calculate the other moments of a random variable. And in Python, we can do a specific case as follows. So I have here mu represents let me first maybe explain this, what I'm doing here, which is, it's a bit slow now. Yeah. So here we are dealing with a Gaussian that has the following expression, which is x minus mu everything squared. And So this would be without the normalization factor, which is the same. This is what, so this is what this Python code is actually calculating here, which is the Gaussian of a random variable, which has an average given by this variable, this coefficient here, the mu coefficient. Sorry, here obviously I think nobody pointed that out, but it's not sigma. Okay, sigma would be the variance, but usually this is written as sigma squared, being sigma the standard deviation. I think I may have, yeah, I also had that wrong here. This should be a square, and as this is inside the square root, it should also be a square. And this is what this code is calculating, therefore. So the probability distribution, or we will describe the probability distribution of a Gaussian distribution with mean mu, in this case 3. And I said sigma, but actually I'm referring to the variance, which is what you need to put in here as the second parameter. So if you use SciPy, you can generate here a range of values. In this case, the range I've defined is like this. So I am going from the mean 3 minus 5 times the value of sigma plus 5 times the value of sigma. That would be the range. So that's approximately minus 22. And that would be around, what is it? Around 28, okay? So this is the range of values I'm considering. And so we defined a normal distribution using stats and giving the parameters we are interested in. And I have defined here a second one with a standard deviation and variance equal to 1. So now what we can print here is the probability distribution. And I'm printing the probability density function at values which are the mean 3 minus the variance minus 5 at the value of the mean. And oh, this should be actually, I wanted here a plus. Okay, and here you have those values, and furthermore, we can also print the probability density function, which would be for those values of x would be what we have here. Now, what a nice thing with SciPy is that if we use the describe, then we can obtain some of those statistics we some of those moments we just mentioned. So by using describe, what we get is the number of points. We get also the lowest value of the probability density function. As it is symmetric, both ends are the same, and this is the value. We get also the maximum, the highest value. And here, so I don't see this, okay. We also have the mean, we also have the variance, and we also have other moments of this variable like the skewness or the kurtosis. So I'm not sure now if the chapter comments on the skewness, but the skewness simply gives you this, whether what we have is a distribution that has a, say, the right tail of the distribution much longer than the left tail. So it would be a biased non-symmetrical distribution, and that's given by the skewness. And in the case of the Gaussian is symmetric, and I guess that is that should be, however, am I doing a mistake here? I would expect the skewness to be 0 if anybody can chime in. I would say that this should be closer to 0. Okay. I will figure that out later. So we can also ask about another thing, which is another statistic. Well, actually, this is the maximum value of the probability density function, which is what we saw here as well. And well, these are the plots. The same probability density function appears, of course, when we have, instead of just one variable, we have more than 1, 2, 3, or n. So let's say we have 2 variables. And then the probability density function is given again by an exponential. And that exponential, or a possible example, would be something like the following. So it's okay, and I am ignoring here. I'm ignoring here normalization, because after all, what did I do here? Oh, because this is not markup. So now it should be okay. Okay, so this would be a Gaussian distribution for a multivariate or 2-dimensional, in this case, probability distribution, or 2-dimensional random variable. So the random variable has 2 components, x and y, and it follows a Gaussian probability distribution. I have a nicer plot somewhere else, which is here, and you can look here at cases of this probability, this multivariate probability distribution. Okay, good, and things. Oh, I know why. I have a dot here. Okay. Okay. So this is how it looks like, and now what happens with this is that if you see it doesn't matter along which axis I am looking at it, they look both equal, but further you can see that actually in this case I can write the probability distribution, or it so happens that this compound exponential is equal to the following.
You want to check that people are still following.
Yeah.
People are still on.
And the other is so. And what this is telling us, so it decomposes into the product of 2 Gaussian distributions, and this is the key relation to say that both components here are independent, because the joint probability distribution decomposes into the product of the probability distributions of each component. And we see that in the plot, it's symmetric. It looks actually equal on each direction that we can look at this plot. Now, in this case, however, let's consider, I'm not sure if everybody can see this. Well, let me see if I think I have a way to
Zoom out, zoom
in. That might be better. So now in this case, oops, is that, oh, yeah. So this still looks very much like the previous one. And notice that what I have here in the exponent is the square of two variables plus another term which is given by x times y with a coefficient. But this coefficient is 1/100, so it's very small. Now let's make it slightly larger by just putting a 1 here and see the effect. Okay, that was maybe too much. So okay, it's still too much. Let me see here. So if you notice, this doesn't look now symmetrical. Okay, so along this diagonal, there is more spread than along this one. It's a little bit twisted here, and this is a result. This result is due to the fact that we have here this product. Having this product here means that we won't be able to decompose it as a product of exponentials depending on each of the components, but there would be as well a term that would depend, an exponential that would depend, let me just write it like this, that would depend on both of them. Okay, so we cannot decompose that into a function of x and a function of y. So in that case that I just plotted over there, it means that they are not independent. Okay. So
yeah, I would put in there like, are people still around, or
I think people are still around. There are a few participants in the video. So okay. I think I would jump directly to discussing the last section, because it's actually independent of the discussion of the probability distribution functions, or discussing the different relationships between independence or marginal probabilities. And actually this discussion on structured probability models contains the rest of the chapter. So let's try to concentrate in the following example. And the following example is it's called apparently the Monte-Hall problem. And it's the setup is the following. So you are on a game show, and the host tells you that you have 3 doors, and behind each door there is either a car or goats. Okay, so if you pick the door that has the car is yours. If you pick any other door, well, I don't know what you will do with the goat, but that's what you may get. So you pick a door, and say number 1, and the host knows what's behind the door, of course, and he opens another door. let's say number 3, which has a goat. Then he goes and says to you, do you want to pick another door? In this case, would you want to pick door number 2? So, and the question is then, is it to your advantage to switch your choice? Put it in another way. Can you do something with the information that the host provided you, in the sense that he picked another door, he showed you what's behind that door? Is that something, an information that you can use? If you want to tackle this by from a point of view of the frequentist approach, which, remember the dice, the number of cases I'm interested in divided by all possible cases, then you are a little bit out of luck, because you can treat it like that. The best way to approach this problem is by using a Bayesian approach. And the Bayesian approach, the best way to think about it is actually in terms of structured probabilistic models, which is, forget about the name and just think on this graph here. So you have the price, which we call it, here I call it Z. It's a random variable from your point of view. You don't know where the price is, and it could be in room, behind door 0, 1, or 2. This should be a 2. Okay, well. Okay, it's freezing a little bit, or can I? No, I can't. Okay, so the contestant, your choice is also at random, because you do not have any information, so you will just pick one. So we have these two variables, and also the host is another random variable from your point of view. He will pick one of the two remaining doors, and you do not know which one he will pick. So we have these 3 variables, and this graph describes a relationship between these variables. Because think about the problem. If you chose door number, what did you choose? Door number 1. For sure, the host will not choose door number 1, because the door that the host chooses, he will open up, and that would terminate the game. There's no point in that. It would defeat the game. So the host will choose one of the other 2 at random. You don't know which one. The price, from your point of view, again, it's also random. But the host will knows where the price is, and certainly he will not choose the door that has the price. So somehow, by the host picking up door number 2, he is conveying some information about where the price is. And the Bayesian approach is the approach that will let us describe this information and even make calculations and answer actually the question of this game, namely, should I or should I not change my choice? So, so here we have then said 3 variables, random variables: the contestant, which can pick these values, the host, and the price can be located in each of the any of the doors. As we don't know anything about where the price is, we will say then that each door has the same amount of probability to be hiding the car. So we give to each door 1/3 of a probability of 1/3. When we are doing things like that, remember, this is the frequentist approach. To any of the doors are equally probable to contain the car, and there are 3 possibilities. So to each of them, we have one case, the probability that the price is behind door 0. It's one case. The number of all possibilities are 3, and 1/3 is the probability we assign. That's a frequentist approach. So even when you are doing Bayesian approach, the frequentist approach is somehow still there. You will be using it. They are not incompatible, and they are not something totally different. The Bayesian approach, and that's, I think, a key idea you have to keep in mind, is simply another way of using another way of dealing with the probability, values. We will see here how. So for the contestant, so the choice you can make, we will also assign 1/3. So this table summarizes these two things for the price and for the contestant. And now we will say the following. Let's assume we have the following table, which I will describe. This table is describing this conditional probability. And this means, assuming that the price is behind the door Z, and that the contestant chooses the door C, what is the probability that the host chooses door H? Okay, so in this case, for instance, imagine that you chose door number 1, so we put a 0 here, door number 0, that the price is behind door number 1. I picked up this table actually from this link here. You can follow it there as well. This seems to me now a little bit awkward. The values they got, I didn't look in detail before, because oh yes, no, sorry, it makes sense, sorry. So I pick, or you pick door number 0. The price happens to be behind door number 0. These 3 values give you the 3 possibilities for the host in this case. And we read it as follows. In such a case, C0, Z0, the probability that the host chooses door 0 is 0. He will not choose your door, that's for sure. It defeats the purpose of the game, we said. Now, however, he may choose then any other door because the price is behind the door 0. So he will not reveal the price either. So either of the other doors is equally likely. That's what is expressing these other 2 numbers. Let's assume that you choose number 0, but the price is behind door number 1. So clearly, the host will not choose the door number 1 because this door hides the price. He will not choose number 0 because that's what you chose. So the only option for the host is to choose door number 2. And the same way we read this 3rd column here, you choose number 0, the price happens to be behind door number 2. The host will not choose yours, so 0 here. The host will not choose, the host will not choose number 2 because that's where the price happens to be. So he has only one choice, he will choose number 1. So in building this table, because you cannot build this table in any other way, okay? If you think about it, you see already that, well, he is providing you some information. And I think it's also very clear, if you would be sitting in the show, if he chooses that door, you know immediately that you have now 50% of chances to be picking the door that has the prize. And exactly this sentence I just said is the key to understand the Bayesian approach. The Bayesian approach is an approach, a systematic approach to change your degree of belief in having the prize behind one of the remaining doors. Initially, you thought it was 1/3, but as soon as the host chooses the other door, you know that what you have is one half of 0.5 probability of 0.5 to pick up the right door. The same way you can read the full table. So, so let's say that the contestant selected door 0 and the host opened door 2. What we need to find is the probability for the prize to be located behind each of the different doors. And that is expressed in this way. So you choose number 0, host number 2. This is an information that you already have. So given this information, what is the probability of the prize being behind door number 0, behind door number 1, or behind door number 2? 3 numbers that we want to calculate now. So the way to calculate it is the following. Here you have this is the probability that we are looking for when H is 2 and C is 0, but here is the general expression. So the probability of the prize being behind one given door, giving the information of the host and given your choice C. This is a conditional probability, and here comes the first relationship. This is Bayes' rule. This conditional probability is always equals to the joint probability, meaning the variable behind the vertical bar and all of the variables to the right of the vertical bar. So the joint probability distribution divided by the probability of the condition. The probability of the condition is everything to the right of this vertical bar. The condition is the information you have. So if we want to calculate this, we need then to divide this problem. First, we will try to calculate the numerator, so the joint probability distribution, and this will be here. And then we will try to calculate the probability of the condition, so the joint probability of H and C, which is here. So let me put the general expression for the joint probability that we are looking here. So how can we calculate this joint probability? Well, I will use again Bayes' rule. And the idea behind the relation I brought here and the use of the Bayes approach is that the only information I have is this table. And this table is giving me the probability of H given Z and C. I do not have the join. I do not have this. But Bayes' approach helps me in dealing with this joint probability in the following way. So consider this conditional probability here. The probability of H given Z and C. This would be the joint probability of these three, which is this, divided by the probability of the Z and Z. So if I multiply this by the probability of Z and C, indeed, I am getting the probability of the joint probability of H, Z, and C. So, but this is an information I do have. This is precisely this table here. Okay, so this is a way to get to this joint probability here. And there is another relationship I will make use of, which is the following. So the chances that the price is behind door number 0 is clearly totally independent of which door you choose, which means both variables are independent, and therefore this joint probability distribution is just the product of the two probability distributions. Okay, that is independence again. Now let's look at the denominator here. This joint probability distribution of H and C. So this joint probability distribution makes use of the section that was saying marginal probability distribution. And again, the only information I have is this table besides the individual probability distribution of Z and C. So that's why I need to write it in this way, because I want to use this table. Let's see how I wrote it. So first, this is a sum over all values of Z. So for Z equals 0, then I write this down, plus for Z equal 1, etc., and so on, which is here. And but what is this? So this is the this is the conditional probability of H given Z and C. That's good. That's what I have here. Excellent. And this is the probability of this condition. Okay, this is Bayes' rule. What is this probability that I'm calculating just here? Well, this would be the joint probability of H, Z, and Z for a specific value of C. Maybe I should have written here some another term which could make this just a little bit sum over set of, maybe I went just one step, I skipped one step, and it would be convenient to have it. Let's see. Oh, I made a mistake here, but I think you already see what I'm trying to write. This is this. So here is the marginal probability in a more clear way. So I want to calculate this probability, and I say, well, this probability should be the sum of all these cases here. What I'm doing here, I'm summing for all possible values of Z, okay? So I am, in fact, calculating, this is the marginal probability of this, where we sum over the Z variable. So there will only remain H and C. And what I do in order to calculate this is using, once again, Bayes' rule in my favor, meaning trying to come up with this expression, because this is a table I know. So if you then do this sum, you have for Z equals 0, you have this expression, for Z equal 1, and for Z equal 2 here. So let's go back and then calculate the specific values for expression number 1 and expression number 2. So we were interested in calculating this joint probability when H is equal to 2 and C is equal to 0. And we need also to calculate this probability when, this probability, which is this, when H is equal to 2 and C is equal to 0. Let's go first over this. This is easy because, well, I just have to put the values here. So let's read, for instance, this value. This value is in the table. When C is 0 and H is 2 and Z is 0, let's go here, C0, H2, Z0. This is it, it's 0.5. So I have 0.5 here. Times this, and this probability is the joint probability of Z and C, but we said already here the joint probability is the product of the two, but each is 1/3. So this will be, in all these cases, 1/9, which is what I have here for the first term. For the second term, this this conditional probability, well, Z is 0, C is 0, Z is 1, and H here is 2. So we are looking at this value, so I have a 1 here. And again, the product, the joint probability of Z and C, which is 1/9. And in the last case, we are dealing with H2 condition on Z being 2 and C being 0, and this is 0, which is 0 I have here. So if I didn't do any mistake, that's 1/6. Then we can go to the expression number 1 and calculate the specific values. And if you do the math, we'll have here one conditional probability for which we do not have yet a number, but this will be 1/3, this will be 1/3. So I have this conditional probability, which is here, times 1/9. Okay, so we just have to go and list all the cases for Z. So if Z is equal to 0, this can be read from here, and it will be one specific, yes, it will be 0.5, sorry, 0.5. And this is, we need to use this, put it in the numerator, this comes in the denominator. So 1/6 is dividing here, and we have then that for Z equals 0, this will be 0.5 times 1/9. So these are the two factors, and divided by 1/6, which is this factor. Okay, so this is this calculation for Z equals 0, H2, C0, and I get 1/3. For C1, if you do it, you will see that you get 2/3, and finally for Z equal 2, you get 0. So what is this result telling us? Well, look, if you chose door number 0 and the host chose door number 2, the probability of the price being behind any given door is not all equal. Actually, it's impossible that it will be behind 2. That was clear. But here is something that, well, improves upon the very first estimate that we said. If the host chooses door number 2 and you chose door number 0, clearly, at least you have 50% probabilities of choosing one of the right doors if you change your mind, say, or if you consider doing again your choice. But what this calculation is telling us is that it's more likely that the price will be behind door number 1. So you improved over the 50-50 that I just said in doing this this calculation. So this is an example of using a structured probabilistic model, a very simplistic case, where we have that one variable depends on 2, and where once we know that the host, the dependent variable, say, got a value, we can update our estimates of any other of the independent random variables. And this is what Bayesian approach really allows you to do, which is changing the expectation, the probability that you expect for a given event once you have gained some information. I just saw that, well, we are a little bit over the time. It's 8:15. So you can use a PGMPy library in Python to do the same calculation of the Bayesian approach. And if you follow here the notebook, you will see that indeed you get those probabilities that we just calculated. I haven't seen any other questions so far. So maybe that's very bad or very good. What remains to discuss is two things, which is well, the section on the information theory, and I wanted to mention the Kullback-Leibler divergence. So let me give you an example. Second. So most of you are familiar with the expression of the entropy of a probability distribution. I will write it down for the discrete case, and okay, so given a probability distribution of a random variable, that should be a lowercase x. We are summing over the values of the probability, the random variable. So this is the expression of the, oh, sorry, I'm missing a sign here as well. Okay, so that this is positive. This is the expression of the Shannon entropy of a probability distribution. And we were saying that the probability distribution contains all the information of a random variable, but it's clear that, let's look at these plots that we have here in the Gaussian case. These are the same two Gaussian distributed variables with a clearly very different parameters of the Gaussian. And here one is more spread than the others. You can imagine that I could reduce the variance of the red one even further, and this would peak even in a more sharp way around the mean, which was 3 in this case. What does that mean? What's the difference between these two cases? Well, clearly, the variations we may expect in the red case are much lower than the variations we may expect in the blue case. It means that in the red case, we know much more about the random variable. Somehow we know much more than in the blue case. And this knowing much more can be quantified in a way that is this. And this is actually, instead of what we know, it's rather a quantification of our lack of information about the random variable and the distribution of that random variable. This entropy appears constantly when we are, for instance, when we try to evaluate when we are testing. Sorry, when we the cost function that usually is used in neural networks, often it's a cross probability distribution. So what we have is instead of just the entropy of one variable, we have the entropy of the joint probability distribution. So basically, it will be the same. Correct me if I'm wrong, but except that we have the joint probability distribution for both variables. Okay, and here we have x, y, and here we would have a log of that probability. Okay. Oops, this is a p here. So let's consider the following case. Imagine that you have a clustering, okay? And that the clustering is, consider this clustering, I'm clustering 5 elements, and I have a clustering in only 2 groups. One contains elements 1, 2, 3, and the others 4, 5. I can calculate an entropy of this probability distribution, which is given by the simply the frequencies approach, in the sense that what's the probability of picking up a element from first group? Well, it's 3 over 5, and from the second group, 2 over 5. And such a discrete probability distribution has an associated Shannon entropy, which is given by this sum, as we saw before. And if you calculate it, you will have 3 cases where it is 3 over 5, and 2 cases where it is 2 over 5. So this is then the value of this entropy of this probability distribution. I still see no questions here, and it's a bit worrying. So sorry. If I happen to have if I happen to have two probability distributions of a given random variable, let's say Q and P, we can assign a an expression of the difference. How different are these two probability distributions? So, is there a way to measure such a difference? And there is, and it's not unique. There are several. And one way the book mentions is through what's called the Kullback-Leibler divergence. So the Kullback-Leibler divergence amounts to calculate the following expression. So what I have is an average. Well, actually, it's similar to the entropy. I'm still using here a discrete case, so I do a sum, and so that will be Pxi divided by Qxi. Okay. This is because it's not code, it's not. Okay. So this expression here, this is the log of the quotient of these two probabilities for any given value, and we weigh this log value with this probability. Notice that this definition, this is a Kullback-Leibler divergence. This is not symmetric. That is, if we swap P and Q, the two probability distributions, that will be different. So it's clearly that this is not the distance in the sense that we are used to of calculating the distance between 2 points in the city. It doesn't matter if you say the distance from the lakeshore to PyTM lab, say, or the distance from PyTM lab to lakeshore, it will be the same. It's symmetric. This is not the case for the Kullback-Leibler divergence, and that's why it's also not called a distance. Remember, it's not a distance. It's simply a measure of both distributions being different. And I've often seen that this is mistakenly used as if it would be a distance. It's not. However, this is only one measure of the difference between these two probability distributions. It happens to have very nice properties, and actually the cross entropy is related to the Kullback-Leibler divergence. So much so that when we are minimizing the cross entropy as a cost function, it amounts actually to minimize the Kullback-Leibler divergence. I think the only thing I would like to add here is that, for instance, in the case of clustering, there is a way to calculate a measure of the difference that is indeed a distance. And this is given by this relation here, where in the general case, it means the entropy of the join variables minus the entropy of each of the variables being the entropy of the join multiplied by 2. This happens to be a real metric. So it satisfies that it's 0 only if both probabilities are equal, otherwise it's positive, but even more so, it satisfies the triangular inequality. So the distance between P and Q will always be smaller than the sum of the distance to a third probability distribution, from P to a third distribution, and for that third to Q, that sum of these two distance is smaller than the direct distance between P and Q. So this is a real metric. So this is not satisfied by the Kullback-Leibler distance. And I think I would rather maybe stop here, or anybody want to add something or make any comment, question?
So I have a question. Here's Florian. So the thing you showed before, it's also known as mutual information, right? Where you have the joint entropy minus the entropies for the single distributions.
You mean this here?
No, the one before you showed in the book, the small d in the book.
You mean
number 5 in the book? The number 5, the equation 5.
Okay, let me.
No, the book before, the other book.
Oh, I didn't show any other book actually, did I?
Just the book you were just talking about before. Here, this book.
Oh,
number
okay.
5, the equation 5.
Oh, the equation 5. Oh, this. No, this is not the joint entropy. So this is this is the entropy of the joint distribution. That's true. So P and Q, where P and Q are here. This is meant for a partition, but in effect, it amounts to calculating the this thing here. It's meant as P from X and Y, and this is the P of X, and this is the P of Y. Say, so this is not the what did you say? The mutual information.
Mutual information. I think
this is not the mutual information. It's okay. It's actually a sum. It can be shown that this is a sum of mutual informations.
I see.
So the mutual information that Q has on P plus the mutual information that P has on Q.
I see.
Yes. And some people refer to it as variation of information. The VI means variation of information for this distance. Okay. And it applies to clusters.
And the other question I have for the Kuller-Leibler distance, so it goes from 0 to infinity, and when it's 0, it shows that they are equal to distribution, or they're independent, or what does it?
No, the 0 would be only when they are equal, because if they are equal, you see that this ratio would be always 1. If they are equal, the probability assigned by Q to X is the same as P to X. So log of 1 is 0, and this is all 0, and it's always positive.
Okay, thanks.
Thank you for the comment.
That's all the questions I have.
Thank you. So I see somebody typing in the chat room. Well, I think I thank everybody for well, for being still around, even though it took me more than an hour to go through only a few of those items. Several people are typing in the chat room. Okay, looks like maybe not questions around. Okay. Maybe, so I thank everybody to, as I said, to still be here around and listening. What I may do before everybody leaves is we did have a couple of questions in the chat room during this week by Marnie, which may be somebody else that has more practical experience with neural networks could chime in and give us his or her insight. And if you browse on the channel on Chapter 3, you will see Marnie's questions related to especially to where would be of use probability distributions like the exponential, or like the Laplace, or like, for instance, the deltas, or Dirac delta, or the empirical distribution. So we had some answers there, but if somebody has something more to add to that, you're more than welcome to do so now. I think maybe for the organizers would also be good at some point to gather some information on how much people have time to read it ahead of the chat or not, in order to guide the following sessions a little bit further. But maybe this we can discuss in the chat room. Okay, so I guess if there are no further questions, that's Marnie, I think. I heard the bird.
I just wanted to thank you very much, Miguel, for your time and effort, and for the notebook. I think it'll be really fun to play with it. So thank you very much. And we will go back to the channel and have a discussion about the interactivity and how to improve that.
Okay. Okay. Thank you very much for the chance, and well, we'll be in touch then.
Yeah. Thanks so much.
Thanks all.